Okay, so I'm going to go ahead and kick this off now. So it looks like I'm able to see folks while I see my previous slides, sort of. But if you have a question during my talk, the best thing to do is just unmute yourself and ask it. You can go ahead and raise your hand, and I'll try and look in chat as well and keep track of that. But this is going to be a little hard for me to do just because I would need 3 screens to do that effectively, and I don't have 3 screens. So I'll bounce back a little bit, but mostly I need to be able to see what I'm going to say next, or my talk will be a horrid mess, and nobody wants that. So welcome. This is welcome to my talk, Understanding Probabilistic Data Structures with 112,092 UFO sightings. I realize that's kind of a whimsical and ridiculous talk title, but it's a fun one, and I think we should learn and have fun at the same time. My name is Guy Royse. I'm a developer advocate at Redis Labs. And so there's a little bit of Redis content in here, a lot of probabilistic data structures content, how they work in detail on 3 of them. And a couple of the ones I talk about are available on Redis. And so I'll talk about how to use those in Redis as well. But this is primarily a talk about probabilistic data structures. If you want to give me a follow on Twitter, that's always appreciated. I'm at Guy Royse. And that's a great way to give me live public feedback and criticize me on the internet, which is what I think the internet is best at. And all the code for all of my talks and this talk as well is at GitHub, at github.com/Guy Royse. So you can get all the code there. And guy.dev is my blog. You too could go read a blog post I wrote a year and a half ago. So that's me. But that's not why we're here. We're here to learn about probabilistic data structures and about this really, really significant number, 112,092. This is kind of a large number, not a huge number in the scale of like the universe, right? There's much bigger numbers in the universe, but it's still a surprisingly large number given that it's the number of UFO sightings that have been gathered by the National UFO Reporting Center or Research Center since the 50s. And so if you break the math down on that, it works out to be, it's been about 70 years since 1950. And so that's, 1,000 a year. That's like 3 a day, maybe 4 a day. That's a lot of Bigfoot sightings. Sorry, I can tell you do Bigfoot talks too. That's a lot of UFO sightings. And this is the number that I happen to have. There's a data set from the New Fork, and this is how many are in it. And the data set is, quite honestly, a joy to read. We've got... some basic keys and values in there. You've got the summary. That's one of the pieces of data. This is sort of the elevator pitch on what the UFO sighting was. 3 saucer-shaped ships. 3 saucer-shaped ships. That's like seashells by the seashore, isn't it? High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Sounds like a UFO sighting to me. You got the city and state. This is where the UFO sighting has occurred. The date times there in convenient ISO 8601 format. You see that this was September 15th in 1950 and was at minus 700 for the time zone. So since that was Oregon, that means it was daylight savings time in effect. We've got the shape of the UFO. So that's one of the things that the New Fork categorizes as the shape. Is it a disc? Is it a light? Is it a triangle? Is it a formation? They've got a whole bunch of different types of shapes. We'll count those shapes later on in the demo. Got a duration, which is mostly for humans to read. They put it in like 15 minutes or 3 hours. So it's, a couple days. It's in those terms. Link to the report, which you go to that URL, you could read the full report, the full text of the report. And some of these are just delightful to read. So, if you're bored and you want to go find something, pick a random UFO sighting and just read it and study it. And then the latitude and longitude where it happens. Now, I've got this data from, I did not download this data from New Fork. This data was screen scraped by a man named Timothy Renner. And he built this massive data set and put it out on data.world. And he went out and harvested the latitude and longitude of the city and state as well. So he could plot out on a chart where all the UFOs were happening. And what he found is that they all were within like 100 miles of U.S. Air Force bases. So to use his joke in my talk, I'm not saying it was aliens, but it was Air Force. So, but this is fun data to play with. He's done a lot of interesting things with it. Another fun fact is that the day of the year that has the most UFO sightings was the 4th of July, because that wasn't a firework. That was clearly a UFO. So, but this is the data we're going to use for all of our examples. And so that brings us to the question, what the heck's a probabilistic data structure? You might be wondering that. If you are wondering that, you are not alone. I did about a year ago, I did a quick developer survey of who had heard of probabilistic data structures. And 58% of the developers that responded in my survey on December the 12th said they had never heard of them. And 22% had heard the term, but that was it. And I suspect some of the people that said I've heard the term heard it right here in my question. Have you heard of thing? Yes, you just used the word. I've heard that term before. Because we're developers and we can be kind of literal minded sometimes. And I'm sure someone just thought that would be funny. But regardless, this gets into this sort of 80% territory of, well, I've not heard of them, or I've heard of them, but I don't know what they are. So we're in this like Pareto distribution levels. We're in 4 out of 5 dentists. Only 20% of the people knew what they were, and only about half of them had actually used them. So if you don't know what probabilistic data structures are, you're in good company, because up until about a year and a half ago, I didn't know what they were. And so I did a lot of research in them and learned a lot about them, and have been doing this talk ever since. This is what I do. I go out and I get something I get interested in. I learn about it in detail, and then I share what I learned. So, but I still haven't told you what a probabilistic data structure is. And well, in order to do that, we need to look at their opposite, the Scully to their Mulder. And the opposite of a probabilistic data structure is a deterministic data structure. Deterministic data structures are the data structures that you know and love. They're the ones that you've been using all along. They're the ones you learned about in data structures class in computer science if you have a computer science degree. Full disclosure, I do not, so I did not learn about these in my data structures class. I learned about them afterwards in my career. But these are the lists and the arrays and the hash tables and the queues and the stacks that we've used. If you've programmed, you've used an array, you've used a list, you've probably used a set or a stack. These are things that are pretty much baked into our languages anymore, and we very rarely have to implement these. Although I remember early on in my career as a C++ developer, we actually did have to build these structures because the standard template library wasn't out yet, and so they weren't available. And so every big project I got on, this first thing was okay, write a linked list, okay, write a hash table. And so this is where I learned about all of these structures. And they're called deterministic data structures because, well, they're deterministic. They do what you expect them to do. If I put a thing in a list, I can go get it back out and it's still there. And if I change that list and I go and ask for that thing that I was there before, it'll still be there. It's reliable. It's deterministic. It does what you expect it to do. And we're going to look at one deterministic data structure in detail because it's got some things that it does that are in common with probabilistic data structures. And that's the hash table. So this is a .NET conference. And so, hash tables are implemented in .NET as dictionaries. If you're a Java developer, we would call these hash maps or just maps. If you're a JavaScript developer, this is everything in JavaScript. It's just an object, right? Ruby, I think, calls them hashes. Python calls them dictionaries, but they're all the same thing. They're all this lookupable key value pairing thing. So if I give it a key, say city, it will spit out the value, Salem. If I give it a key that it doesn't know yet, it'll return null. If I set things with those keys, it will populate them, and then I can pull them out with those keys. So I can store things with a key and assign them a value, use that key to pull the values back out. We know how to use these. They're dictionaries. We've used them before. And so here we got city state. This is our UFO data here. And we're going to show how that works under the covers, how a hash table works under the covers. And first, we're going to look at what the heck's a hashing function, because they're called hash tables because they make use of a hashing function. And a hashing function is something you've probably heard of as well. And what it takes is a seed number that you keep constant and data. That can be a little bit of data here, like the 6 bytes that make up the word Scully, or it could be, like a 2 gigabyte ISO file, some big ISO image for a CD or something like that. It could be an entire database. It could be any data we want. And the hashing function takes those two things and squashes them down to a signature or a fingerprint that's a single integer, usually like a 64-bit integer or a 32-bit integer. And it does so deterministically. It does it consistently. So if you give it the same data and the same seed, it will always give the same value. But you cannot take that value and get the data back. You might be thinking of hashing functions like MD5 or SHA. And those are hashing functions, but those aren't the ones we're talking about for hash tables. Those are used because they're cryptographic hash functions and they're more secure. They're harder to reverse engineer, so you can't figure out what the data was from the number that's generated as easily. Whereas other hashing functions, like we're going to use murmur hash in some of the code samples I have. We may not take a look at them, but this is what I use in all my code samples. It's optimized for speed. The cryptographic hashing functions are secure, but they're slower. And if we're accessing a hash table, and this is like a basic data structure we're using in our code, we want it to be fast. We want to Ricky Bobby it, right? And so we're using those sorts of hash functions instead. It's not about security, it's about speed. And so a hash table uses these hash functions, and it does it by hashing the keys. So a hash table is an array of buckets. And these buckets are actually linked lists. And we'll get into that a little bit when we talk about collisions. But it's an array of these linked lists. And what we do to add a value to it is we take the key and we run it through that hashing function. And we'll get this big 64-bit number or a 32-bit number. But our array is probably not whatever max in is for a 64-bit number. Our array is, because that'd be a ridiculously large number. We wouldn't have enough memory. And so in our case, we're going to make our hash table have 10 items. The array in our hash table have 10 items. And then we could expand and contract that as we needed to, and we just have to reindex everything. But we are going to use a smaller one because we don't have a lot of things and because it fits on the screen. And so what we do is we take that city, that string, the key, we run it through our hashing function, and then we modulate that key with the width of our array. So our array is from 0 to 9. It's got 10 elements. So modulus of 10 will give us a unique number, give us a number between 0 and 9. And so city gives us a 1. And we put the word Salem in the bucket in position 1. If we want to read it, we do the same thing. We put in city. We hash it, we do the modulus 10, we get an index, and we go look in that bucket. And so this is how the hash tables work. So let's add a second thing to our hash. Here, let's add the state. So we add the key of state, hash it to 10, and we get a 4 now instead of a 1. And so we put the state in the bucket in position 5, in position 4. So now we have 2 things in our hash table. But sometimes we'll get a hash collision. So shape, we are arbitrarily saying here, is going to have a hash that ends in 1 as well. And so if we try to put it in position 1, there's something there already. And this is why these buckets aren't just buckets of strings or buckets of whatever our type is. They're buckets of the buckets are linked lists. Because what we store in that linked list is the key and the value. And so in the case of city, when we added Salem, we added an item to the linked list of key city, value state, or value Salem. Now that we have shape, we see that there's already something in the linked list, and so we append it to the end, and it's got shape and disk. And so this is how we handle hash collisions. We keep a list. When we go to read from it, we can pass in city, get that index of 1. We go to the linked list, we walk that until we find the key with city, and then we return it. If we had passed in shape, we would get the same index. We would walk it until we got the key of city, which would return disk. If we gave us something like, summary, which we haven't added to our hash table yet, it would go to that list, walk to the end of it, never find it, and return null. And so this is how hash tables work. And excuse me. It's kind of neat the way it works. Because figuring out what our index of is a constant time operation, right? It doesn't matter if I have 10 entries or I have 1,000 entries. Finding the particular linked list is a constant time operation. It takes the same amount of time no matter where it is. I don't have to walk through them. I can just go right to it because the hash tells me where to go immediately. And this is one of the advantages of the hash table is that lookups have a big O of 1 time complexity. And when we select deterministic data structures, we're looking at them from a time complexity point of view. In other words, do they have constant time, O of 1, like a hash table? Or do they have, O of n, where it's a, number of items determines how much time it spends in there? And we trade that off against space complexity. Is this take up more or less space? Is the space complexity O of 1, or is it O of n? And so, like these trade-offs, we make them with let's see, we'd say like a hash table has good time complexity, but its space complexity is it uses more space because it's got a lot of empty space in it. So you've got this array that you've allocated, and you're not using all of the array. Whereas like something like an array list, it's got really good space complexity. It's never any bigger than it needs to be. It's exactly the size that it needs to be, no bigger. But it's slower to use because you have to walk that array list or that linked list to find all the elements. And so these are trade-offs we make when we select the deterministic data structures we're going to use. And that's not completely the whole picture because they're not always trade-offs. Sometimes there's just different capabilities. Like you've got a linked list and an array. A linked list can be as long as it needs to be, but it's slow. An array is exactly the size that it is, no bigger, no smaller. And accessing the items is fast, but you can't resize it easily. So resizing is expensive. Whereas a linked list, resizing it is not expensive at all. And so these are, it's more complex than just this or the other. There's capabilities where in this capability, the space complexity acts like this, or the time complexity acts like this. And so the decisions are more complex than just time, speed versus space, right? And it turns out there's actually a third thing in addition to time and space that we can have this complexity around, and that's accuracy. We can make trade-offs in accuracy to conserve space and to conserve time, to make things fast and to make things small. And you might be thinking, well, why would I want a data structure that is inaccurate? I want it to always tell me the truth. Well, if it always tells you the truth, then you want a deterministic data structure. But there are times when you scale such that you cannot take advantage of that. If you are, say, Facebook, and you've got 1 billion users, and someone signs up and you want to see if the username's taken or not, you cannot simply do a select star from users where username equals username you desire and get any kind of performance. It's just going to take too long to walk through all those users. And so you could use a probabilistic data structure that is much smaller and faster to access, but it lies to you 3% of the time. And at scale, that could be a very reasonable trade-off. You could use that as like a gatekeeper. Go to this thing here and tell me whether I can do it or not. And then if it tells me something that falls into that I'm not sure scenario, go check to be sure, but otherwise don't. And so it lets you scale in ways that you can't. And you've actually probably used these in a way that you're not don't really think about. But this is a good analogy to a probabilistic data structure, and that's the Humble Jpeg. This is a picture of the Devil's Tower. I think it's in Wyoming or Montana. I can never remember which, but it's definitely in Close Encounters of the Third Kind. And this means something, right? And the Devil's Tower, aside from being a beautiful national monument, this picture of it being quite beautiful, it's a JPEG. And so what the JPEG does is it takes each of these individual pixels right here, right? So like one of these pixels we're looking at is blue, but it's probably the wrong color of blue. But it's close enough. And this is because the way a JPEG compresses, it loses some of the data and then figures it out after you decompress that image to show it to you. And that lost data, that lossiness, is good enough because I can't distinguish the two shades of blue that are different in that one pixel. And so it's a little bit lossy, but good enough. That's kind of what probabilistic data structures are a lot. They got an accuracy rate where they're not perfectly accurate, but often that's good enough for your purpose. A lot of the probabilistic data structures can be thought of as sets with peculiar properties. So a set in the set theory idea is, you can add and remove and get things from a set. Here we've got a set of shapes that are totally not the shapes on the Redis logo. They're totally arbitrary and picked at random. We got the star, the square, the circle, and the triangle. We could add something to that and say add a nonagon, and now there's a nonagon in there. And we could remove the triangle. We could get the triangle and say, what's in this data set. Lots of things we can do. Probabilistic data structures tend to restrict what types of operations you can do on a set. So you might be able to add things to it, but not be able to remove or even query what's in it directly. But you still might be able to, say, get a union of two sets and then check the cardinality of those. And so they're like restrictive sets. One of the things that we can test from with a probabilistic data structure against a set is we can test for membership. This is asking, is this thing in the set? Yes or no? And, or I guess probably yes and probably no, because they're probabilistic, right? So here we're saying, is the square in the set? Yes, yes it is. Is the nonagon in the set? No, no it's not. Membership. It's an easy concept. Is it there or not? Cardinality is how many things are in the set. It's counting the unique elements. And so here we have 4 unique things in our set. We have a star, we have a square, we have a circle, and we have a triangle. So there are 4 types of things in the set. And so it has a cardinality of 4. If we were to add a nonagon to this set, it would have a cardinality of 5. If we were to remove the circle, it would have a cardinality of 3. And so the cardinality is just how many things are in the set. That's all it is. But it's not quite that, because it's how many unique things are in a set. Because there's another thing, which is frequency, which we can also ask of a probabilistic data structure, which will tell you how many of each thing is in a set. So these are both ways of counting, but it's like counting classes versus counting instances. Cardinality is counting the number of classes in our code base. Frequency is counting the number of times that that class is instantiated. And so here we've added the star 5 times, we've added the square 4 times, we've added the circle 6 times, and the triangle 3 times. And so the frequency lets us get those counts. It shows the frequency of those elements in the set. Cardinality is still 4, but the frequency is showing it's the other way of counting things in a set. And with frequency, you can derive rank. You can say, well, which number is the biggest? Which number is the second biggest? But you can ask a set to get the rank of the things in them without necessarily knowing the count. There are probabilistic data structures that allow that, where you can say, tell me what's in first, second, and third place, but I don't know how many there are. That might be all you need to know. So I just need to know the rank. I don't need to know the specific counts. What's the top 5 most commonly used, clickbaity, headlines that you won't believe after you look at this one weird trick, right? Rank. You're ranking these things. And then, so we looked at all these sets, but these are just sort of things you can ask of sets. But another thing you can ask of multiple sets is you can compare them. You can take a set and say, how similar is this set to another set? And we're going to look at that one in particular with minhash and Jacquard's similarity. But it's a way of saying how similar is the first set to the second set, because the second set's missing an element, or to the third set, which is missing 2 elements. And so we can get metrics on how similar sets are to each other. And we can do that in a probabilistic fashion. So if you want to use probabilistic data structures, there's a lot of choices out there. Here we've got a few. The ones in blue are the ones I'm going to talk about in detail. Some of these probabilistic data structures are available in Redis. If they are, they're marked with a little red dagger. If you are using core Redis, Hyperlog logs out there already, it does cardinality of objects, and so it will count like unique objects up to like billions and billions and billions of them, but only takes up 12K. It's kind of cool. Cuckoo filter and Bloom filter are things that do membership. They're similar. Cuckoo filter is a little more sophisticated. The Bloom filter is one we're going to look at in detail. Count sketch and count min sketch will give you frequency. I don't know a lot about QGIGEST and TGIGEST, but they are ranking probabilistic data structures. We're going to look at detail in Heavy Keeper, how they work. Heavy Keeper, it actually counts and ranks, but the counts aren't super reliable. And so, but the ranking is a lot more reliable. We'll look at that in detail. Heavy Guardian is a variety of Heavy Keeper. Min hash and sim hash do similarity. Specifically document similarity. And so we're going to look at how min hash works in detail as well. And for the ones that have the little dagger on it, I'll show you how they work, and then I'm going to show you how you can use them in Redis instead of coding your own. So we're going to look at Bloom filter first. Excuse me for a second here. I'm going to get a drink. I'm getting a little phlegmy. A Bloom filter is a probabilistic data structure that's part of Redis Bloom, which is a module that extends the capability of Redis. Bloom filters check for membership. You can do two operations on your set. You can add to it, and you can check for membership. And it can answer in two ways. It can say no or probably, which is a little weird. It doesn't say yes and no. It says no. Definitely no. It can say with certainty that a thing has not been added to the set. And when you ask if something has been added to the set, it can say it's probably been added to the set. Bloom filters are a fixed size. So when you create a Bloom filter, it's the size that it is. If you fill it up with too many values and exceed that size, if you build a Bloom filter that's optimized for say 1,000 entries and you cram 2,000 in it, you'll start getting a lot of false positives. It'll start saying that everything's probably in the set. But they're fast. It's big O of one operation to add or query the Bloom filter. So very, very fast. It's made up of two parts. You've got some hash functions with seeds. Remember these from the hash table. And you've got a bit array of a fixed width, which is also kind of similar to how a hash table works. And we're going to do pretty much the same thing we did with a hash table with this. We're going to take a string and we're going to run it through these hash functions and set some values. So let's see what that looks like. So here we've got a UFO sighting. We want to make sure we haven't seen these UFO sightings before, or we have. If we've seen them before, then we don't want to re-index them. And so here we have one entitled Megatron in the Bushes. This is my favorite UFO sighting of all the ones that I've read. These guys got out of their car somewhere out in the desert in Arizona, and I'm not sure exactly why. Probably take a leak, and they're out there, and they hear this sound in the bushes out in the desert. This sounds like Megatron from the Transformers. That sound, right? Yeah, I apologize for that, by the way. But yeah, so it's Megatron in the bushes. They heard that, and so they freaked out and they hopped in their car and then took off down the road, and this bright light like chased them 50 miles down the road. It's a great story. But it's Megatron in the bushes, and we want to know if we've seen this before or not. And so we're going to add it to the Bloom filter when it's submitted. And so we take Megatron in the bushes, we take that whole account, and we run it through those hash functions and get some signatures. We get some numbers. And we modulus them with the width of the Bloom filter. So our Bloom filter has a width of 10. And then we get indexes. And like the hash table, we are going to put something in there. But in the hash table, we modified our linked list. In the Bloom filter, we're just going to flip the bit. So 5, 0, and 6, they all get set to 1. So that's how we add to it. That's all there is to it, adding to a Bloom filter. To read from that Bloom filter, we go through exactly the same process. We put Megatron in the bushes, we get our numbers, we get our 5, 0, and 6, and we go and look at all those indexes in the Bloom filter, in the array, and if they're all 1s, We just AND them all together, and if they're all ones, then hooray, Megatron in the bushes is in the Bloom filter, probably. It's probably there. If any of them are zeros, we know that it was not in the Bloom filter because nothing could have come in to set it. Let's add another UFO sighting to our Bloom filter. This one is happened right here in Columbus, Ohio, where I'm based out of. I seen a UFO when I was about 13 years old. It was in all uppercase in the original in the text in the data set, so I preserved the yelly case. And in here, we're running that through this same process. We're taking our seeds, we're taking our data, we're running it through the hash function, we're getting numbers, we're modulusing them with the width of our array, and we're getting different indexes. But we have a collision. So 2 and 1, we haven't used those before, but 6 has been used. But that's not a problem because the other 2 are unique. If we go in and say, I see a UFO, and to read it, we're going to get 2, 1, and 6. We get 3 ones back, so they all, that's all true, so probably in the Bloom filter. If we go back to our Megatron in the bushes, it gets all ones back as well. It's still happy. And this is actually why we have multiple hashing functions, is so that when we have collisions, they don't hurt us. We can collide, we can have some overlap in our collision, but as long as we don't have a total collision, then our Bloom filter still will be accurate. But it's not a guarantee. And so this is why there's that probably there. This is probably in the Bloom filter. So let's look at a place where we add and read with a total collision. Here we have investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. And in this case, we get 0, 1, and 6. And all 3 of these have been used before. Some of them by ICN-UFO and some of them by Megatron. And so if we add this to the Bloom filter, it doesn't change the state of the Bloom filter. And so it doesn't do anything. And if we go to read it, it's going to respond and say, it's in there. Now, if we had asked, is it in there, and we hadn't added it, it would have been exactly the same. And this is why it's probabilistic. This structure doesn't have any way of knowing whether Bigfoot was in there or not. If the BFRO folks, if their sighting was in the Bloom filter before or not, it only knows that these bits are set to high because all the data gets hashed away, and we just have these bits set. And so if we had asked the question beforehand, it would say it's probably in there, and it would have been a false positive. If we had added it and then asked the question, then it would have said it was in there, and that would have been a true positive. But we really don't know which it is. Probabilistic, right? And this is actually why when you fill a Bloom filter too full, it just starts returning false positives all the time. Because once all these bits here are 1, once they're all 1, it's always going to return true for everything. And so you can't overfill these things. So a good question might be, how do I know how to figure out how big these values should be? How wide should I make it? How many hash functions should I use? Well, there's a couple formulas here which are kind of intimidating looking, but really aren't. It's just algebra. And so you've got 2 functions or 2 that you can use, and you can do substitution to figure it out. But basically you can say, you know how many items you want. I want to put 1,000 items in my Bloom filter, and you know what your acceptable false positive rate is. And so you can pick a random number of bits, solve for K, shove K into the formula, solve for P, and say, is this acceptable? And you can loop through that until you get it. Or you can do the algebra and actually substitute K with all the M divided by N times the natural log of 2 in all those places, and do that as well. But you still have to, and then go back and solve for K and everything. But it's just algebra problem. It's not that hard. And you could do that. There's an online calculator that does that as well. That's very convenient. But of course, I just use Redis to do this because it has a Bloom filter built in, and it's in the Redis Bloom module. And so you can just tell it your error rate and your capacity. So here we call bf.reserve with Redis Bloom. We give it a key that we want to store these things in, UFO shapes. Give it an error rate. We find 0.5% of error acceptable, and we want to store 100 items. To actually use that Bloom filter that you've set up, you can call bf add and just provide a key and then the item to add. So here we're going to add a disk. You'll notice that bf.add UFO shapes disk returns a 1. bf.add UFO shapes light returns a 1. And then this is because it has modified the state of the bloom filter with adding those. On the next one, we've got mad for multiple add. And light's already been in there, and so it returns a 0 because it hasn't modified the state when you added light a second time. But teardrop did, so it returns a 1. But mad just lets you add multiples. You can actually use mad all the time. You don't need to use add. Syntactic sugar. To actually use the bloom filter, there's 2 commands to actually query it: exists and exists. And it's really simple to use. You just say, is disk in the bloom filter? And it'll say 1 or 0. And exists just does that with multiple. So is light and triangle? Light is 1, triangle is 0, because light is in there, triangle is not. So that's bloom filter. Any questions so far?
There's a question in the chat. Someone asked, to avoid collisions, is it a good idea to apply multiple hash functions?
Yeah, I probably have answered that already. But yes, but well, it's not to avoid collisions; it's to reduce the impact of the collision. So with the bloom filter, the more hash functions you have, the less impactful a collision is. But then the wider your bit array has to be, and so you're trading off between those two things. And then your probability of, and those all determine your probability of collisions. So more hash functions can be better, but aren't always better. So it's complicated. Now the formulas kind of do that for you. So let me see if there's any other questions over here. Yeah, the UFO stories are fun, aren't they, Meg? Good resources for data structures in C#. One of these I've implemented in C#. I can't remember which one. I've mostly, I don't have any great C# resources for this. I'm not a day-to-day .NET developer, so I did do a stream where we coded inefficient data structures in JavaScript with Brendan Enrick. So you can always go check for those. They're up on YouTube. So min hash determines set similarity between documents. So is this, how close to this document is this other document? This you could use for like maybe determining if something is plagiarized, or if to see whether it's changed enough to bother re-indexing it, if say you're a search engine. And to do set similarity between documents, we have to do set similarity. Set similarity is done using Jacquard similarity. And Jacquard similarity just takes the cardinality of an intersection of two sets divided by the cardinality of the union of those sets. So what that means is that in this case, Scalder and Molly have seen UFOs in different states in the Union, and they've seen them in New Mexico and Ohio together. That's the intersection. The union is the other 8, and so 2 divided by the other is all of them. So and 2 divided by 10 then gives you 20%. So 20% similarity between where Scalder and Molly have seen UFO sightings. It turns out they have in common New Mexico and Ohio, so that'd be Area 51 and Hangar 18. So checks out. To do this with documents, you could just take all the words in documents and make sets, but that would just only show you how similar the language was. Like you couldn't just say, we is one of the elements in the set, and notice is one of the elements in the set, and 2 is in the set, because the intersection is going to be very heavy because we're all using English. And so to turn a document into a set so that you could do this sort of comparison, we need to do a process called shingling. And shingling is breaking it up into overlapping trigrams. So here we've got our first trigram is we notice 2. That gets added to our set as we shingle this document. Then we go notice 2 hour. So see, they're overlapping like shingles on the roof of a house. And then 2 hour left. And so we're creating this big set of trigrams. And then we can take this set of trigrams from one document to another and compare those sets. So here we've got 2 reports from Scalder and Molly. Skinner wants to see how similar they are, to see if if they're actually doing independent work, if they saw the same thing. He's trying to check their stories against each other. And so he's going to use Shingling and Jacquard similarity to do that. And so here we can do that same intersection over union with the cardinalities of those, and find that these reports are 0.636 similar, so 63.63 repeating similar, so about 2/3 the same. And so Skinner's reasonably happy that they're seeing interesting things, but at the same time are seeing different things. So this works great, except it's got one big flaw, which is that it's slow, very, very slow. We're comparing strings to strings. If we wanted to, say, compare Skalder's report against, 1,000 reports, well, that's going to take a lot more time. These reports probably aren't a single sentence. They're probably documents. They could be hundreds of pages long. And so comparing these is really slow. And so what you can do instead is you can calculate a min hash and then compare those min hashes. And so the way you compute a min hash of a document is you take all the shingles that are in your set, all the trigrams, and you run them through hashing functions. And so in this particular case, we have we notice 2 is run through each hashing function. So we notice 2 is run through, in this case, 3, and then it generates a number, which is the first column in each of these little ribbons. And then 2R, notice 2R is the next column and the next column and the next column. And so this first row is a hash of every value, every trigram in the document for that particular hashing function. And the next one is a hash for every trigram in the document for the next hashing function. And then of those sets of hash trigrams, we pick the lowest value, the minimum one, the minimum hashed value, the min hash, for each of those sets. And so we got 3 hashing functions. We end up with a set of 3 numbers for the min hash of that document. Now we can pick more hashing functions or fewer hashing functions as makes sense for what we're doing. And so Skalder here gets 233, 143, and 102. We do the same thing for Molly, and we get different numbers, but some of the numbers are the same. And so then we have 2 sets of 3 numbers, and we can do a Jacquard similarity against them. And so once again, we take the union and the intersection, we take those cardinalities, and then we divide. And here, this is determining that we have a 0.5, 50% similarity. And so this is a lot faster, and we can save these hashes, these minimum hashes, and use them in the future. So we only have to calculate that min hash on that document once, and then we can compare it against new ones as they come in. Now you might have noticed that we went from about 2/3 to 1/2, and that's not because min hash isn't accurate. It's because we didn't choose enough hash functions to get the precision, a comparable level of precision. Our resolution was a little more chunky because of the particular number of hashing functions we chose. We could just choose more, and then we could get the same granularity. So if you're looking at those numbers and thinking this didn't perform nearly as well, it's like, well, that's because it's an example, and I only used 3 because it fit on the screen. But I also wanted all my math to work. So that's min hash. We're going to look at top K next, which is actually heavy keeper and min heap.
Can I ask a question real quick?
Sure.
About min hash? Just like the example you used, I was wondering if that's used in like I guess like police investigations, kind of like to compare people's stories to each other, see like validity of things. Like when would that be used in real life, I guess? So
min hash, I believe, was created by Google. I don't know that the police do this. They probably, my guess is they don't, because the stories might be similar, but the selections of words would be very different, right?
Mm.
But Google, I believe Google's the one that created min hash and sim hash, and they used it to figure out whether they should re-index documents or not, and to compare documents to say, does this page have a copy? This site have a copy of the document on this other site, to find out where content was being duplicated.
Okay, so, cool.
And so that, I'm sure, saved them a lot of cycles.
So, gotcha. Thank you.
Yeah, very, very happy to help. So top K, which is heavy keeper and a min heap. Top K is all about ranking. it's finding the top K items. So like the top N things, the top 3 most clickbaity headlines. This is one we have in Redis. It's made up of a min heap and a heavy keeper. And we're just going to focus on the heavy keeper because it's honestly the more interesting part. Min heaps are a little more established data structures. Heavy keeper, once again, it's using hash functions, right? So it's got a selection of hash functions with a seed, and it's got an arrays of buckets. And when you create a heavy keeper, you say, I want my buckets to be, say, 100 wide, and I want 3 sets of buckets, which means 3 sets of hash functions, or 5 or 12, or whatever you want. And it will create this empty structure. Each bucket, each of those is an array of buckets. Each bucket contains a spot for the hash value and a count. And the hash value is the result of the hashing function. The count is the number of times that's been incremented. And then otherwise, this is, in many ways, this is kind of like the hash table again, isn't it? So just like there's a lot of these structures are just variations on hash tables where you can handle collisions in interesting ways. So a brand new heavy keeper has hash values of null and counts of 0. And so when we go to use a heavy keeper, we go to add something. And so here we're adding the word object. We want to track the shapes of UFOs that are encountered. And so we take that string object and we run it through our hashing functions, and we get a number, like we always do. And then we run it through, we modules it with the width of our hashing function, 100 or 1,000 or 5, whatever width you picked. And that'll give us an index. So here we get indexes of 2, 1, and 6. And so what we do is we populate index number 2, index number 1, and index number 2 of that location with the count and the hash that we have. Because they're all 0 and the hash is null, and we go in there, we see there's nothing here. So we go ahead and say counts 1 because we added object, and here's the hash for count that was computed. And we do the same thing for each row. Then if we want to go add it a second time, we go through the same calculations, we get the same numbers, only this time there's something there. And so we look and see that that thing there is the same as our hash. So the hash value in position 2 on the first row is 5062. That's what we computed. So let's just increment the count. So now all these counts are set to 2, which is accurate. We've added object to this heavy keeper twice. If we want to go read it, we just reverse this process. We put an object, we get our indexes, we look and say these hashes match at this location. It gives me 3 numbers back. I take the biggest one. In this case, they're all 2. So I report out that there are 2 objects in the heavy keeper. And it works. So far it's accurately counted. If we want to add something different to the heavy keeper, this is where it starts to get interesting. So here we're adding light, which is another popular UFO shape. What shape was it? It was just a light in the sky. Light gives us different indexes, but some of them collide because we have hash collisions. And so for the first 2 rows where we don't have a collision, we just do the same thing we did with object. We go out there, we find that there's nothing in position 1 or position 2. We set the hash, we set the count to 1. Everything's great. But in the 3rd row, right down here, we've got a collision where in position 2, there's something there already, and the hashes don't match. So what do? Well, what happens is we might decrement the count of this particular 1442 from 2 to 1. And there's a chance of doing that. And we're actually going to use a random number generator to do that. And we calculate the probability. There's this probability of decay formula, which is a magic number from 1 to around 1, at least bigger than 1, but about the size of 1. And so I picked 1.05. And we take that to the power of our count as a negative number. So our count is 2. And so 1.05 to the power of negative 2 is going to give us 0.907. So there's a 90.7% chance that we're going to decrement the value from 2 to 1. Now, as this gets bigger, that likelihood of being decremented gets smaller. The count as it goes up, it's a negative exponent, so it shrinks down. And so that means that once the things get heavy, once they get big, they are less likely to be thrown away. So it keeps the heavy things, heavy keeper. So we're going to say decay has occurred, and now we just decrease the value. Now, if we go to read light from here, we'll get results for the first two rows, but we won't have a match on the third row. But we've got two numbers, and we take the max, and it's 1, and so it tells us accurately what's in there. If we query object, we get 3 results back, 2 2s and a 1, and we just take the maximum, which is 2, and so it's still accurate, even though one of them is being eroded a little bit. And every time we add something to Heavy Keeper, we update the min heap with that count and that key. And so if object comes in and it's got a higher value than 54, then 54 gets removed and the new one gets put in there. And then when we want to ask what are the top 5 items in this top K structure, then we just look at this min heap. If we want to do count queries, we can go ahead and go to the Heavy Keeper itself. So top K is something that's available on Redis, and I've got a demo, but I'm not going to have time to show it because it looks like I've only got about 2.5 minutes left. I apologize for not being able to show the demo, but so here we'll call topk.reserve to set up a top K structure in Redis, give it a key, and we say how many things do we want in our min heap? We want the top 3 whatever. So 3 is that number. That's the K. We give it a width. That's how wide our structure is, and then we get a depth. That's how many hashes we have. And we give it a decay. That's at 1.05. In the case of Redis, it uses the reciprocal of that, so it's 0.9 in this case. I put 0.9 in there. I don't know what the reciprocal of 1.05 is off the top of my head. So to add things to top K, you call topk.add. Here we've added 3 disks, 2 teardrops, and 1 light. But the command's really straightforward. If we want to go ahead and query, is this thing in the top K or not? It will look in that min heap, and we say, is disk in the top K? We call topk.query, the key, and then disk, and it says 1 because it is. We can ask for the count, and it will use the Heavy Keeper to figure out that count. And so we added teardrop twice, so it returns 2. And if we ask for topk.list, it'll give us all the items that are in the min heap, and say these are the top 3 items. And so, coding one of these yourself is a lot of fun and interesting, but there's one already. You don't need to do it. So, unfortunately, I'm going to skip the demo because I'm at the time limit here. Here's some resources to go check out. A lot of blog posts that I used in helping put together this talk and really learning these things. This is a white paper on Heavy Keeper, which was a very dense read, but interesting. Here's the UFO data if you want to go play with it. Here's the site the data came from if you want to go UFO splunking. And then here's some stuff on Redis Bloom on our website. And then there's a blog post by one of my peers on using top K to count the words in War and Peace. I work at Redis. We got a Discord server, discord.gg/Redis. If you want to ask me questions, you can join there. I'm always on there. And so, if you ask me something 3 a.m. Eastern time, I'm not going to answer it, but I'm normally on there. Check out our forums, sign up for stuff. Here's a QR code. It gives you all the codes and slides and everything. I swear it won't rickroll you. And my name is Guy Royse. Thanks a lot for attending my talk.
Fascinating talk, Guy. It's the most out-of-the-world thing we've seen at Philly.net.
all the puns, right?
Absolutely. Still looking for the truth.
Yeah, it's out there.
So we will see you in an hour or 2. I'm going to end your recording, and everybody else head off to another session.